Hello, this is Mr. Huff, and I want to talk about calculating the coefficient of drag for our parachute project. Did see some errors and that sort of thing, so I just want to go through a basic example with some numbers I pulled out of the air. So let's say that you are going to build a parachute device, and you cut a sheet of plastic that is 2 feet by 2 feet. So that's 24 inches by 24 inches, or 576 inches squared. If you go to Google and ask it to convert 576 inches squared to square meters, you'll get that it's 0.372 meters squared. One of the things I noticed in the assignment is that some of you had very alarmingly high numbers for your area. One of them was 192 square meters. That's larger than your house. So you need to pay attention to that. So one of the other things too is I see people mixing measurement units, and that's leading us to errors. So you need to take your square feet or your square inches or your square centimeters and convert all of those to square meters. And you do need to realize that a centimeter is not the same thing as a square centimeter. So that's one of the things you need to be aware of. This was a big area where people made mistakes. So get everything to common units. When you found your mass, if you were lucky, you had a kitchen scale. If you weren't so lucky, then you had to build a balance. And I provided a table that showed information from the U.S. Mint showing how much mass each coin has, and you could build a simple balance. And you might discover that this device that you built was 30 grams, and then you have to convert that to kilograms, so 30 divided by 1,000, and you get 0.03 kilograms. It is important, again, to get everything in standard units. Just real quickly, let's talk about the errors I saw mostly. I saw people mixing System International and customary measurement systems, so we had inches and kilograms mixed up in the same calculation, and that is going to lead you astray. And I'll go back and reference the Mars probe, where they had customary units on part of the design and System International units on the other part of the design, and it got all the way to Mars and crashed into the surface, costing $125 million. So please don't make a mistake like that. Get everything to System International measurements that are standard for our formula. Also, I saw a lot of people making mistakes with the area unit conversion, where they were going from inches to meters and using the conversion for an inch to a meter rather than a square inch to a square meter, and that was causing problems. And also I saw people making mistakes with calculating the mass and weight, going from mass to the drag force. I saw one calculation that had their weight listed as pounds, and they had an unreasonable number of pounds for what they were dropping, what their design showed. So be sure you're getting everything to common units. Here, let's talk about drag force. So the numbers we have are 0.03 kilograms. The acceleration due to gravity is 9.81 meters per second. And we know that the drag force in the situation of a parachute is equal and opposite to the force of gravity. So that means we just use the force of gravity calculation, which is mass times gravity. So 0.03 times 9.81. We get a drag force of 0.2943 newtons for a 30-gram device. The other thing that's given to us is the density of air. This is just assuming air standard pressure and temperature at sea level. We're just going to use this one. It's 1.19 kilograms per cubic meter, and that is not a letter P, it's a Greek letter rho. It looks the same as a P. So that's the density we're going to use for air. And then velocity, I just kind of picked out some numbers that I saw in some of your examples that you turned in. A really common distance was about 2.5 meters, and a really common time was around 2 seconds. So I'm using 1.8 just for the sake of this calculation. So to find our velocity in meters per second, we take the y displacement divided by the time, or 2.5 divided by 1.8, and that gives us a velocity, an average velocity as the device falls, of 1.38 meters per second. Let's compare that to Freefall, and I gave you this calculation just to show how fast it would be going if you just dropped it without the parachute. So we are using gravity and the y displacement in this case. So the final velocity is the square root of 2 times g times y. And you plug those numbers in, and you see that that object is going to be falling about 7 meters a second when it hits the ground if it's in free fall. So if you look at what our velocity is at 1.38, we have slowed it down substantially. Let's talk about surface area now. When you look at a flat sheet and then you tie it to your object and you drop it, it's going to assume a hemispherical shape. And I showed you in the notes how that means the surface area that's functional is reduced to about half. So starting from our flat sheet to the parachute shape, we're going to just use a rough estimate that it's half of what we started with. So that means our surface area is 50%. So we take our surface area and divide it by 2, and we get 0.186 meters squared for surface area. So let's look at the calculation now. The coefficient of drag is equal to 2 times the drag force divided by the product of area, the density of the air, and the velocity squared. So if we take our numbers and plug them in, we see that it's 2 times 0.2943 divided by 0.186 times 1.19 times 1.38 squared. We only square the velocity, not the whole thing. And that gives us a coefficient of drag of 1.39 in this example. So most commercial parachutes are made to be between 0.8 and 1.2 for the coefficient of drag. So the higher that number is, the more drag that the parachute is going to produce. And it is common in this lab to see some of these going up into the 3, 4, and 5 range depending on your design. So you shouldn't be seeing 0.000 something. What that is telling you is you are on something slippery. It's like that small number is unrealistic. That tells you you made a conversion error somewhere. So go back and check your math. All right, so that's all I have for you today. And please take a moment to answer the follow-up questions.